Hi everyone, welcome back to the evening session on blockchain based auditing and verification of data stored in the object storage. So I am a cloud storage architect as part of the IBM systems and development lab, and I have been joined today by my colleagues Vijay, Archana, and this is a project which we started late last year as one of the exploratory projects in evaluating and understanding usage of blockchain based technology and platform to solve some of the problems in the object storage domain. But as you can see, when I present the topics, you can maybe relate to and also find other areas within storage where similar technology could be used. And I also want to acknowledge some of the key contributors to the projects with many ideas. We do have Sandeep Ramesh, Rishika Kedia, and Subbi Nalasivan. Okay, so first question is who have not heard about Bitcoin? Everybody knows Bitcoin. So one of the key technologies behind Bitcoin is the blockchain. So when I say blockchain, simply blockchain is nothing but a database, and it can store a set of transactions, and once the data is stored, what we call it within blockchain is blocks. The data cannot be modified or deleted, right? So let me quickly look at what's happening today in the industry is that, for example, if you are doing transactions, it could be any kind of transactions, cash transaction or assets transaction. You have various parties in the transactions. You have party A, party B, you have auditors, and you have banks. And today everybody is maintaining a ledger on their own, and they do make note of all the transactions which they are doing. And finally, there has to be a process that takes so much time for those transactions to be committed. What is that called? What happens, everybody maintains a ledger, so what is the problem with maintaining a ledger with everybody, their own ledger with everybody? Coordination. Yeah, I think that's a great point. Coordination. The process of reconciling the transactions across various parties is what you call as coordination. It takes a lot of time, cost and money. And by the time all this happens, you spend so much money. And many times you have conflicts between various parties saying, did you send it, or you didn't send it, and all of that time. All of that gets very expensive. That is one of the key challenges that blockchain is trying to address, is that can we have a centralized ledger where all the parties can record the transactions? So if you see the right hand side, that's what it is. There is a centralized ledger in the cloud or somewhere, and you have all the transactions which are recorded in the centralized ledger. And all the transactions are recorded in that. And then the interesting thing is each party has a copy of the centralized ledger. So it's not that you have one ledger. You have one ledger logically, but physically you have every party have a copy of the same ledger. Now you have a question that what if somebody says, I made a transaction, out of the four parties, one party says you never made a transaction. It's possible, right? So that's where I'll talk about how blockchain addresses those problems. But it's interesting to see is that when you have a centralized ledger where all the transactions are updated between all the parties, and also you have a copy of it, there is a way within blockchain that you cannot refuse a transaction which has been committed. You can do that, but there is going to be a huge penalty or a cost in order for doing that, in a sense that within the blockchain, you have the series of transactions, and each box there, we call it as a block, and each block has a previous block's address stored there. So essentially, it is a cryptographic one-way hash function that was spoken about earlier today. Some of you would have attended the session in the afternoon. The cryptographic hash function, one-way function, is essentially you can take a message. It's a set of, it's a transaction encoded as a message, and then you can convert into a hash, and that hash is an address of each of the block. So the second block essentially has the address of the hash of the first block. The third block has the hash of the second block. So now you have a series of blocks which are running over. Now the problem is if somebody has to say, I didn't make the transaction, the challenge is he has to essentially say that all the transactions that happened before did not happen, which is a very costly proposition because pretty much it's like you are up against the whole network. Everybody else believes the transaction happened. And you have a ledger. Yes, you have a ledger. You can go and delete the block because it's your own ledger and say the transaction never happened. But everybody else have the transaction reflected. How are you going to fix everybody else's transaction?
So I'm not very familiar with this technology. The technology comes up is when you commit a transaction in this asynchronously replicated to all.
It's all asynchronously replicated. So within the Bitcoin, it takes about 1 hour for the Bitcoin transactions to be committed, because the way they do it is in fact they have a set of nodes called the mining nodes, and they give a mathematical challenge. So all the nodes have to solve that challenge and then commit the transaction. The time it takes today is about 1 hour, but the thing is more and more getting added to the network. It's going to be much more secure. The transactions are going to be much more secure. And again, when you come and talk about the international transactions today, takes about 3 to 4 days. If you're sending over a bank to bank kind of transfer, it takes 3 to 4 days today to get confirmation. Here it takes about an hour. So still orders of magnitude faster than the traditional transactions. But yes, there is still a challenge in order to ensure that all the meaningful nodes, a blockchain network can have like thousands and even millions of nodes, as you correctly said. It takes time for everybody to replicate and to say, yes, I got all the data. Today it takes in the Bitcoin network, it takes about 1 hour. But we are going to talk about a use case where we have like a private ledger where we may not have that many participants. So the commit will happen much more faster. I think we have a question in the back.
How costly is it to maintain a copy with each of the party? So there can be n number of parties, right? So if number of party increases, similarly, the cost of maintaining the copy with each party also would increase. Correct.
What you're asking is correct in the Bitcoin network. So the people who are responsible for committing the transaction are called the miners, and each of the miners have an incentive to do that, because as you said, it could be a huge database. In order to maintain and spend money on the database, they in fact get credit in terms of Bitcoins. They do get payment, receive payment as one of the incentive as part of that. So that is a...
And is there some form of master copy or...
There is no master copy.
No master
It's
copy.
all totally peer-to-peer. There is no master, there is no control. All the networks, all the nodes can come, join, leave anytime. There is no master copy.
So if suppose there are 3 parties involved and 2 of the party loses their own copy, and the only copy that has remained is with the remaining left party, so, and he can modify it, right?
No, the network tends to be large. In case of Bitcoin, it won't be three participants. We are talking about really scale, like millions of nodes and joining and going. So that's where the system works much more efficiently.
Okay.
If you have only 3, as you said, it's very prone to frauds and and misuse.
Okay. Thank you.
Okay, so you have that, and then the critical part of it is that blockchain is one of the underlying technologies. There is a question here.
One more, sorry.
Sure.
So, when you're saying this, these are all connected over the network, right?
Correct.
Now, if there's a single database, if I lose connectivity to that database, only that database is inaccessible. But now, there are multiple networks, multiple providers.
Correct.
If there is one of those links that is missing, what happens to the transaction? Does it get committed or does it not?
No, see, there is a consensus protocol among majority of the nodes. So the moment the consensus is reached, irrespective of whether other nodes within the network committed or not, the transaction is still committed.
So you're saying that if there is a network outage between any 2 nodes, it doesn't lead to the transaction not getting...
It is designed for to manage network outages, partial, things like there is some connectivity is lost to a set of nodes, or within a geography there is no access. So it is designed to kind of manage some of those scenarios as well.
Mathematical brute force quorum kind of thing. They use that mathematical brute force quorum.
Yes. You have to solve the challenge within that time to prove that you committed the transaction, and all the nodes in the network are doing the same thing.
It's possible that you have fork, but then it will be eventually consistent.
Yes.
Quick question perhaps. So regarding bullet 3, and perhaps I'm piggybacking on one of the previous questions, isn't the storage cost going to be enormous here because every participant is getting a copy of the entire database is what you've
Correct,
said?
correct. So see, it's actually, we are not storing the data, we are only storing the hash of the data.
Okay.
So the storage tends to be smaller, but still, when you're talking about billions of such hashes, still you have a storage problem. So yes, the storage tends to be bigger than
So
what
then
you would
data is at a central location. So if only the hashes are sent to the participants, so the data is all at a central location, then what is done in the middle? Where is the data then?
So they don't send any data. See, it's when you say transaction, A is sending $500 to B. So that transaction becomes it goes through a cryptographic hash function, and then you have a meaning to that. I mean, so there is a structure in which that transaction is recorded. So and then all you have is the encoded message. There is nothing like.
So that makes sense for financial transactions, but I thought maybe you're going to address it
Yeah,
later
I'm
for
going to
object
talk about
storage. Okay.
It's interesting. So
Fine.
we are not going to store data in the blockchain. So
All
yeah,
right, fine.
I'll talk about that. Okay. So so that's about the blockchain and Bitcoin background. Now let's come to the blockchain, various variants of blockchain. So we have the public blockchains. There are many of them. Bitcoin is one of them. It's operating a blockchain and the cryptocurrency, and it's public. So anybody you can create your own client, key and certificate. You can join the network. You can do transactions. There is a public key, private key infrastructure based public network. Anybody can join and leave at any time. There can be miners who are part of the committing the transactions. You can become a miner also, and if you have an infrastructure, you get bitcoins as part of the incentive because you are kind of one of the participants in the network. But there is also another kind of blockchain that you can operate is the private blockchain. So these are blockchains that you can operate within your enterprise, or you can also include your partners and other providers, and this is only within your network. So it's not a public network, nobody can join and leave anytime. So there has to be an authentication model. That's what we implemented in our prototype. There's an authentication model to join into the blockchain network and do the transactions. So in this particular work that we have done from a prototype perspective, we have taken a private ledger, a blockchain platform, and we have instantiated that, and then we have configured that to work with the object storage example. And then, so there is a trust factor which comes in there, because in the public ledger, there is no authentication of the person. Whomsoever who is it sending, who is it receiving. So that's one of the concern behind Bitcoin and the cryptocurrency, is that the government regulations at some point of time may come in and have a crackdown at the transactions. So that is one of the biggest concern they have, because there is no authentication model. Whereas in the private ledgers, you can authenticate the person saying, oh, this person is from this company and he is responsible for doing this transaction. That is perfectly fine. You can plug in the authentication model. And the consensus model also, I know Subhajit asked the same question. In an asynchronous kind of network, it's going to take a lot of time for the consensus to emerge. A network, again, it cannot be reliable, especially the internet. But here in the private case, you have a smaller network, right? You can probably run like 4 or 5 nodes, and the nodes are under your control. So the consensus protocol can also be changed to a model where the transactions can be immediately committed compared to how the Bitcoin operates. So that's what we are saying here. It is a replicated, shared and replicated ledger where all the transactions are recorded. The contract, so once again you asked a good question, right? When it comes to currency, the transaction model is different, but whereas when you're talking about other kind of transactions, the blockchain allows you to specify a transaction in your own language, as long as all the network participants agree to that language. So that's where it is interesting. So what is that contract is up to you. You can define that. So I'm going to talk about what is the contract that we defined for this particular work, but you are free to define your own contract. And then the privacy, and then the validation. I'll talk more about it. So now the question is that there are many such blockchain implementations which are around the world. Bitcoin is one of them that we are all aware. There is a blockchain network called Everledger, and this is a blockchain ledger, is a platform for registering the genuine diamonds and to prevent conflict diamonds, or what they call as blood diamonds, to be circulated within the market. So whenever there is a diamond, they certify the diamond, and then you can sell it and it can go through various parties, but you can still track the genuinity of the diamond, when was it manufactured and the original certificate date and all of it. So that is now available. Everledger is the name, you can Google for it. Also in Sweden, what we found out is there is a blockchain based land registration and asset transfer platform. Essentially means is that you have a land, or you have a property and you are selling to somebody, and then X, and X is selling to Y, and Y is selling to Z. So it keeps on going. And we always have this property challenge. At some point of time, somebody can come and claim this is my property, right? Which is a problem, which we thought is a problem only in India, but it appears in Sweden also they have the same problem. So they are implementing a blockchain-based land registration and asset transfer platform to establish a digital trust between between the citizens within the country for selling and buying properties. Now the question comes is, can we use the platform to manage the life cycle of data as an asset class? So this is a question. See, our own answer is yes, but we can debate about it, because one of the things that has been said about blockchain is that it can be a very useful platform, especially the question that you asked, like there is cost associated in running the platform, there's storage cost, there is operational cost and all of it. Can it be a viable platform to manage the life cycle of data? So the answer is yes. I mean, for this particular work, let's assume the answer is yes, because that's kind of the basis of this work. And we're going to talk about how we can use blockchain to manage the life cycle of the data. So, and just to give credit to other work which is happening in the industry, there are so much work which is happening in the industry, but I just want to highlight one such platform. It's called Storage. It's called Storj, but it's pronounced as Storage, which makes it a little bit difficult to, if you're talking, are you talking about Storj or Storage? But this is a blockchain-based, end-to-end encrypted cloud storage platform, which is based on peer-to-peer. Essentially, if you have free drives, free capacity in your drives, you can rent your drives to the Storj platform. So you have to install the software and configure and say, oh, I have 100 terabytes of my disk drive capacity, which I'm going to put it as part of this cloud storage. And then the storage platform will essentially pool all those disk capacities over the internet across millions of devices and create a one large pool of storage, which can be used essentially as like object storage, how we have various object storages in the world. And all the data is essentially encrypted at the client side and then sharded into various chunks. And then these chunks are stored in various disk drives across various hundreds of nodes. So in that way, only the original person who is holding the data can put all the data together, but the data tends to be split and stored massively. What is interesting is that the Storj, if you can go to the website, you can see that their costs are almost 50 to 60% cheaper than the regular cloud storage kind of cost, because they're able to pull a lot of free capacity together, and it's a peer-to-peer network which is based on blockchain. And they are using blockchain internally to identify where the chunks of data are stored, and they do have replication and a lot of other schemes. But essentially, it's a blockchain-based database which is kind of central to the architecture of this distributed cloud storage. Sure. No, I'm not. So we are not doing anything with Storj. I'm just giving an credit to work which is happening in the industry where blockchain and storage domain are coming together. We are not using Storj anywhere. So our work is, I'm going to talk about it in the upcoming chat. So our work is more related to the object storage that is commonly available. Things like we have IBM Cloud Object Storage, the Amazon S3, Azure Blob Store, and OpenStack Swift. In particular, the prototype we have done is going to be on the OpenStack Swift, because I will talk about it even in yesterday's session. Some of you would have heard about this flexibility that OpenStack Swift has called the middleware, which allows you to extend the functionality and add your own custom logic. So we are going to use that. I'm going to talk about it in the upcoming chat. But essentially, object storage, we all know. I mean, that's why I said, this is a storage forum, so I don't want to say what is object storage. So we have what is not object, who is not using object storage, because actually everybody is using object storage. The key aspect of object storage, as we all know, is it can store billions of objects and it can scale, and it's very much based on a very simple application access protocol with HTTP APIs, get, put, post, delete, and all of it. And then it also allows efficient sharing of data with various parties within. It can originate somewhere, it can be consumed by many other participants, because the HTTP is a very flexible protocol. So what is the problem that we have taken for this particular project is the use case is that we want to be able to verify and the audit that is stored of the data that is stored on the cloud. So cloud object storage, there are so many examples that we discussed. So you as a participant, you as an enterprise or a company, you can store a lot of data. So now you have been storing data for many weeks or many months. Now how do we know what data, the data that you have has not been tampered with on the cloud? Secondly, how do we know, essentially the entire life cycle. Who is assuming you create an object, who is deleting the object, who is updating the object? There is no actual update of the object, but when you update the object, you can create a new version of the object. So you can have many versions of objects. And who is deleting the objects, or who is even creating the original objects? And are my objects tamper-proof? So it's important to understand that the technology that we are discussing is not going to prevent from somebody tampering with your data. Assume you store the data in the cloud. The cloud storage provider have corrupted the data or tampered the data. We cannot prevent that, because the cloud storage provider is totally in control of their storage medium and the data. They can go and take your object, they write some garbage to it, your object is corrupted. There is no way to prevent it. But what we can do using this prototype model, we can tell is that we can tell where the data is tampered with. I'm going to talk about that in the next chart, but we can tell where exactly it got tampered with, and we can prove that where the data corruption happened. So that is what makes it interesting from this project perspective. So what we did is that we have taken the OpenStack Swift as a platform, object storage platform, and then it has this middleware concept. So it's a very nice concept where you can extend the functionality by adding your own behavior. So what it means is that every request, it's all REST API request, right? Like get, put, or post and delete, which comes to the OpenStack Swift server, can be interrupted by your middleware. So both the request and the response can be overridden by your own logic. So any request that comes to the server, you get essentially a callback, and you can do whatever you want, and then you can pass it back to the OpenStack Swift, so it will do its own logic. So you have complete control over all the operations. So what we did is we added a blockchain integration middleware to the OpenStack Swift, which intercepts all the incoming get, put, delete, post, all the requests. And for each of the requests, we register the transaction in a blockchain database. There is a open source blockchain platform called the Hyperledger. So this is a open source project which is backed currently by the Linux Foundation. It's been co-developed by IBM and a number of other companies. You can Google for it. So we instantiated an instance of Hyperledger platform, blockchain database, and the integration middleware essentially records all the transactions in the blockchain. Now what happens is, interestingly, that you have, like, for example, object A is created and the object A is updated, a new version maybe is created, and then the object A is deleted. So every transaction that you do on the object storage, you create a new block in the blockchain database, and it's all chained together, and you keep on creating. Like if you have like a billion objects and you are doing like a million transactions, so you will essentially have like a billion into billion blocks here in the blockchain database. So it's going to be huge. Yeah, there is cost in running this. So once you updated it, once you created it, what really happens, what is interesting now is, assume you have the earlier question that you have, right? So what we store in the block is very interesting. So Vijay has more idea on it. So Vijay, we store checksum of the object, and the authenticated individual who is performing the request, and the timestamp, and user, what operation is performed, whether it's get or put. And we also store some of the other information, right? There is a set of objects per object related information which is captured in each of the block. And the interesting thing is it also has a checksum. So now assume you created an object, it has the checksum captured there, and then the object is updated. Now the updated object's checksum is also stored there. The object is deleted. So now the interesting thing is, since each object has a cryptographic hash representing that particular object ID, you cannot create the object again because it's been deleted already. If you create it again, it will conflict with, you already created it, you updated it, you deleted it, now you cannot create, you can create some other object but not the same object. It's a similar thing like you have an object, it's been created and it has the checksum stored. Now when you are performing a get, if a checksum doesn't match, now you know when you created an object you have this checksum and you have not updated it because there is no update record from you as a user. So it is a cloud platform which should have corrupted the data. So you can essentially prove that whatever data, because the cloud is the one which is acknowledging the checksum, and after that if the checksum is not matching, then you know where exactly the data is corrupted. And also it's very interesting that you have multiple organizations, you have like partners, everybody sharing the data, and they are doing a lot of read and writes and updates and deletes. You can also track who is doing the reads and updates. Suppose an employee goes and deletes a container, a bunch of objects are gone, you can essentially find out when it was deleted and who it was deleted. So it also, one is it provides you that integrity of the data. Second, it also prevents you from tampering with the data, and it also provides you a platform to audit all the data in the cloud. So the interesting thing that I want to talk about how it works is there is a algorithm that blockchain uses internally called the Merkle tree. Go ahead.
I had a question on the previous slide. So you could have done the same using, say, some other database. So are you going to talk about how this compares with perhaps doing it with other databases, or maybe?
Absolutely. So his question is, can we not do it in the other database like MySQL or Postgres or something? You can do it with other database, but let me explain this chart that will tell you some of the advantages of doing with blockchain. See, one is with respect to scalability. Blockchain is a very highly scalable model where you can keep on adding more nodes and linearly you can scale it. But today you can argue that there are other databases also which can scale. But let me talk about this chart. So let's look at this. So the cryptographic hash function combined with the Merkle trees provides a wonderful way of ensuring the tamper-proofness of the data. So how is it done? You can see in the bottom of that. So this is all the blockchain transactions, the blocks. So each one is a block. And what you have here, the Merkle tree, the way it works is that you take the L1 and L2 block, and then you do the hash of both the blocks, and that's what you store in the block above. And similarly, you take those two blocks, the hash 00 and the hash 01. I'm not sure whether it's visible from the back of the room, and then you hash it again using the same function, you get another hash. So that's that node. And then you have the root, what we call as the Merkle root, which is essentially the hash of the top two nodes. The beauty of this is, you can read more about it, is that at any point of time, if you have a conflict with the data, when you compute the hash, it won't match with the root hash. If you change the data like L2, it won't match. And you can do the same thing with the database, but the problem with the database is you need to analyze all the nodes to ensure the verifiability. But here, if you have a data corruption in L2, all you have to take is the L2 and the hash 01 and the hash 0 and the root. So there is a path which is of log n. See, essentially, if you want to do the same thing without Merkle tree, you have to traverse all the nodes. So if you have n nodes within the graph, it will be order of n. But here it's order, log n, because you are, if your tree could be big. I mean, this is a very small tree. You assume you have like billion blocks. Your tree is going to be very big, and now you have a challenge of verifying the entire tree versus you have a path which is very quickly you can go to the root and verify that the hash doesn't match with the root, so it's a transaction which is not invalid. Yes. So that's the beauty of Merkle trees. Every time you add it, the hash has to be computed to the root and then added. So it is a mathematically verifiable, the blockchain itself, that is what in the initial chart when I said tamper proof, is that once you add it, if you change it, you know which one is invalid. Because the whole tree is a cryptographically computed, mathematically verifiable tree. And there is also a path you can identify which are the invalid paths. Because any node could be wrong. Any transaction could be invalidated. But you can identify the clear path to the root saying what all will be impacted compared to searching all the nodes.
But when you add a node, the hash will change at the root because you are combining two nodes and then hashing it.
Yeah, I mean, so we need to, I'll give you the link to the Merkle trees. It's a very complicated algorithm. Yes, yeah. The hash functions, it has a lot of math. Right.
You said that for every transaction, that hash will be computed till the root, right?
Correct.
So it means, or whether it will already, it is having the previous node's hash.
Yes, it already has the previous node's hash.
So that if you are calculating that, likewise, the previous node will have the
No.
previous.
See, the only reason for you to go up to the root is if you have an invalidation or a conflict. Otherwise, there is no need to traverse up to the root.
So in that case, if any one node has got invalidation, the whole tree that will become fully invalidated, right?
Yeah, but you can identify it, right? So which is invalid, you can identify it.
Yeah, we can identify. Just one modification itself will make the tree invalid.
That's why we said, see, within the blockchain, you don't have a single ledger, you have multiple ledgers. So the chances of one ledger going like an invalid transaction is very high, but not all the nodes.
Yeah, correct.
Yeah, so that's what the key is. Okay. So yeah, so so I've already been told it's only 5 minutes, but I think the key message here is that that blockchain presents an interesting set of use cases, and I think as from a storage domain, it's very interesting to see how we can adopt blockchain into a variety of use cases. What we have presented is maybe one of the ideas, and I'm sure we can, wherever there are opportunities of multiple parties involved, especially with cloud, with storage getting into the cloud, we have always, two parties. You have one entity sending data to another entity, and there is a trust comes into the picture. We feel that blockchain could be a very interesting technology to solve problems related to trust, integrity, verification, and auditability of data within the storage subsystems. Sure. No, Vijay, do you want to answer that? It's a prototype. We haven't measured throughput at scale, but you had some challenges with the database scalability, right? Can you want to talk about it?
Till now, the transitions, like one of my friends is working on the blockchain also. He told me that you can make around 10 billion transitions in the blockchain. It has also a scalability problem, because the hardware support and all these things, it is right now in the phase of development, Hyperledger blockchain. So, but for our prototype, we are able to migrate 1 million objects, and we are able to get.
No, see, in order to answer your question, the data which we are storing within the blockchain database is very small. On a per transaction basis, it is only a hash and few of the properties, that 5 or 6 properties about object that we want, even that is hashed and then stored. So the amount of data per transaction is small, but only if you scale to millions of them, then you will suddenly have the challenge.
Sure. For each transaction that you are acknowledging and committing, you will need to do updates to your Merkle tree.
Correct.
So I'm sure you will not return a transaction till your Merkle tree updates are accounted for. So if updates to the Merkle tree are the bottleneck, given that it's a hash function, and if you are using say SHA-1 or
SHA-256, yeah.
SHA-256. So you will have to go over the data how many, 64 or 65 times, right, in order to kind of get it. So if the data size is huge, your computation is going to be huge. It's going to consume a lot of CPU, and so you will be delaying the response of your transaction.
I think his question is on the middleware side. We are doing the blockchain transaction, apart from allowing the original data path to do the actual object write or read. So his question is that adding to the performance challenge of in the middleware path, because you are doing the additional blockchain, because are we waiting for that commit to come before we actually pursue the IO part? I think that's an interesting question. Actually, in our prototype, we were waiting.
Yeah. In middleware, actually, we are not blocking. We are whatever response comes from the other middleware, we will just bypass, and we are getting information, and we will do the async operations. So it won't block the whatever storage operation is there. So, but the thing is, the response take time. But something has happened, then administration will be getting notification. In the security thing is like. The security thing is like administration who is auditing the thing, like something is happening, he will get the notification, something like that, it will happen. Merkle tree is like itself is the part of the blockchain. So whenever the transition is done, it will happen inside that only. We are not considering how its blockchain is updating. Okay, in blockchain actually itself, transition is verification, and all these processes take time. Because if the nodes are increases, then it takes time to update in each node.
Okay, I think time's up, so we'll be available outside. So if there are any questions, we can certainly take it outside. Thank you, everyone.